Okay, thank you very much for the introduction and for the invitation here. So it's a pleasure to be here. Can you hear me at the back? Okay. I'll be giving a kind of survey on contact processes, which are a specific model of epidemics, and specifically on networks. So this is meant to be an introductory lecture. I don't know the backgrounds of the audience, and I'm sure there's a wide range of backgrounds, and the language may differ between areas. So if something I say is unclear, do feel free to interrupt. It's better to make sure that we are using the same terminology. Okay. What I aim to do in the next couple of hours is to give an overview of some results in this area. There will be, there won't really be time to go into proofs, so it will mostly be a survey of models and results, maybe a bit of intuition, and the very occasional sketch of a proof. So I'll start by introducing the process we are going to study. Or even before that, let me start by just introducing some terminology on the kinds of graphs or networks on which we are going to be working. So we are looking at a graph G with a vertex set V and an edge set E, and V is going to be finite or countable. And E is a collection of pairs of vertices called edges, and these are all going to be undirected. We are only going to be looking at bounded degree graphs. So if the graph is finite, of course, this is the degree is necessarily bounded, but even in the countable case, we are only looking at bounded degree graphs. So some examples. Particular things we are going to look at are the integer lattice in d dimensions, so that's Z2, TD, which are deregular infinite trees. So the three-regular tree would be and so on. And then we'll also look at finite graphs. So these are some examples of the kind of graphs we are going to look at. Okay, and on all these graphs, what we are interested in is a very simple epidemic model known as the contact process, or the SIS epidemic. So we'll denote this process by psi t. And this is going to be a continuous time Markov process. On the state space, which is subsets of the vertex set V. Intuitively, you should think of psi t as the set of vertices that are infected at time t, so that's the epidemic. And how does the process evolve? Well, every infected vertex can infect its neighbors at some rate, and also it spontaneously can recover from its infection. And as soon as it recovers, it's again susceptible to infection. So that's the model. Okay, so that's the intuition, and more precisely, more formally, so from any given state, psi t has two possible transitions. You can go to psi t union a vertex x. So one more vertex can get infected. First let's look at transitions where there's a recovery at x. So you remove one of the vertices from the set of infected vertices, and this happens at rate 1. Okay. So in time dt, there's probability dt at each vertex that that vertex recovers. And you can also have one more vertex getting infected, and this happens at rate lambda times the cardinality of this set, the number of vertices y in psi t which are adjacent to x. So each of your neighbors y, if it's infected, if it's in psi t, infects you at rate lambda. So lambda is the infection rate, and each of your infected neighbors infects you at rate lambda. Okay, so this is the basic model we are going to be looking at throughout. So any questions on this model? Hope it's completely clear. Yeah. Yeah. It's very nearly the same. So the question was, yes, so this is a Markov process, meaning it's memoryless. So no matter how you got to a certain state, this description applies. What happens in the next dt time interval is independent of everything else that happened before that. And it's very closely linked to Poisson processes. In just a moment, I'm going to give you a construction of this process which involves Poisson processes. Okay, so thank you for the question. And one more bit of notation. So we will write psi at to denote the process with initial condition A. So if you start with an initial infected set A, we'll write the A on top to denote this. Okay. And so there's one observation we make about this process. So psi t is a process on subsets of the vertex set V. What happens if you hit the empty set? The empty set is absorbing. So if ever the set of infected vertices is empty, then infection can never reappear in the graph, just from the description. So as soon as you hit this state, the process stops. And the kinds of questions we are going to look at are starting from some arbitrary initial condition. Do we know whether you always hit this particular state, or do you can you avoid it forever? And if you hit it, how long does it take? And questions of that form. Okay, so I've given a verbal description of this process. Okay, so I claim there's a Markov process with this description. Is this really true? Is the process well defined? On finite graphs, there's no issue. It's well defined. There are no problems with this description. On infinite graphs with countably many vertices, this is not entirely obvious. There are different ways of showing that it is well defined. I'll now give a construction of this process without giving detailed proofs. I'll hope to convince you that it is well defined. And the way we are going to construct, yeah? Sorry?
What are x and y?
Oh, x is just some vertex. So x is an element of V, and the same for y. So xi t is a subset of infected sites. You can add so one of the sites x from that set can disappear, meaning it becomes healthy. And this happens at rate 1 for each such site. They all independently recover at rate 1. Also, a site X, which was healthy, become infected. So you can go to this new state, which is the original infected nodes plus X. And this happens at rate lambda, each of the neighbors of X infects X. So at rate lambda times the number of infected neighbors, it goes to the set of infected vertices. Okay, and here's a graphical construction of the contact process. And this is very useful. So what we are going to do is we are going to, for each vertex in our graph, we are going to draw a timeline. So time goes up here. You start with some initial configuration. So this, so the first vertex is infected. A couple of them are healthy, which are blank circles, and the filled-in circles are infected. Okay. Now, on each timeline, we put down a unit rate Poisson process. So there are some random times at which recoveries could happen if this node was infected. Otherwise, they may not. So there's an independent rate 1 Poisson process on each timeline. So for the timeline corresponding to each vertex, we put independent rate 1 Poisson processes because recoveries happen at rate 1.
What's a Poisson process?
Okay, so a Poisson process is a continuous time counting process. You start at time 0 with count 0. As time progresses at random time. So, okay, so it's a model of from physics of radioactive decay. You're counting the number of radioactive decays in your sample. These happen at random times, and every time one of your atoms decays, you count one more. So the times between these counts are independent exponential random variables with the same parameter as your Poisson process. So that's one way to think of it. Other properties, irrespective of what's happened so far in every time dt interval, there's probability dt of this event happening. Or if you look at some interval of time and you want to know how much your count has increased over that interval, then that's a Poisson random variable with parameter equal to the length of the interval. So these are all equivalent descriptions of a Poisson process. So you put a Poisson process on each vertex, and also for every edge in the graph, you put Poisson processes at rate lambda of directed arrows. So if there's an edge between the first two vertices, you might have some arrows at rate lambda in each direction. So at rate lambda, you have arrows which tell you when attempts to infect happen. So let's say this is the one-dimensional, this is Z1, the graph, then you might have some arrows like this. So for the moment, let's not even think about infection and susceptible. We are just going to put down these events, these crosses and these arrows. And having put them down, so this is our probability space, these crosses and these arrows. Then I'll go back and think about how the infection spreads. For now, we just put down, we forget about what the states of the nodes are. We just put down these Poisson processes on the nodes and on the edges over time. Okay?
Is there a reason why you assume these are Poisson, or is it just a baseline?
That has to do with this model. So if these were Poisson, they exactly describe this model. If they were something else, they would describe some other model there. Okay. Okay, so now having put all these down, given an initial condition, we can describe what happens at any time. So let's say we want to find out what happens to the second vertex at this final time t. So we started at time 0, at time t, what happens? Well, we start following from all the initial infected vertices, or we can start from t and go backwards and ask, so what needs to happen for vertex 2 to be infected at time t? There has to be a path from here down to an infected vertex, and that path has to avoid all the crosses, and it can follow all the arrows backwards in time, in the opposite direction. Yeah. So from here, you can't avoid this first cross, so you have no way of being infected at time 0. From here, you can keep coming all the way here. The arrows are the wrong way. Maybe let me draw the arrow this way. Do I have colors? Okay, so from vertex 4, you can keep coming down. You can't go, you have to go the opposite way on arrows, so you can get down to this arrow, down to this vertex. This happened not to be infected at time 0, so there's no infection here, etc. Okay? So this construction, from this construction, you can find out which vertices are infected at any time given the initial condition. And there are some things about this construction which are very useful. And from which certain properties of this model are much clearer than they would be if you tried to prove them analytically. So one property is monotonicity. So let's consider two initial conditions, a set of vertices A being infected initially and a set of vertices B. A is contained in B. Then at any future time, the set of infected vertices starting from A is contained in the set of infected vertices starting from B. Okay, so this is a stochastic description, but in this particular realization of it, this particular construction, it's an almost sure property. Okay. So if you start with more infected vertices, you always have more infected vertices.
Just got some statements. Are you using random points you're using?
Yeah, so we are coupling on the same realization. So both of them have the same realization of these. Otherwise, you have to make a stochastic version of that statement. If they have different randomness, you can't make this exact statement. Then you have to make a probabilistic version of the statement.
They be close to each other. Can you make something high probability?
No, you'd have to say that. So if you order subsets, then in the usual partial order, then you can say that that the stochastic ordering is maintained by the evolution of the epidemic. So so the probability of being in a certain set, which is stochastic, which is okay, so you know what I mean. You have to make statements in terms of stochastic ordering rather than a deterministic ordering property. You can also see that if you increase the rate lambda, then the infections increase, and again, you have a bigger infected set if you increase the infection rate. So monotonicity in lambda. And similarly, if you increase the recovery rate, you have smaller infections. Okay, our recovery rate is fixed at 1 because it's just a time scaling. So I didn't want to have two separate parameters there. And also, if you want to couple different realizations with different values of lambda, this is a natural way to do that. So you can construct versions of these on the same probability space in an easy way. So you see monotonicity. You can also see subadditivity. So if you start an infection in state A union B, and you look at which vertices are infected at time t, this is a subset of what's infected starting in A alone, union what's infected starting in B alone at time t. So there are some properties which become quite apparent from this construction. By the way, I mentioned that the process is well defined, so that's also something you can show using this construction. So what might be an issue with the notion of the process being well defined if you're in an infinite graph? The issue could be that to say what's the state of a vertex at time t, you have to follow everybody who could have influenced you between time 0 and t. And if you can have influence propagating from infinitely far away, then you have to make sure that you have defined things consistently, that different ways of looking at what happens infinitely far away don't give you different descriptions of what's happened to a vertex at time t. From this construction and the assumption that the degrees are bounded, you can simply count how many paths can influence you. Well, how many self-avoiding paths of length n are there to any vertex? If the maximum degree is delta, there are delta minus 1 to the n such paths. Now, what's the probability that influence could have propagated from some vertex n steps away to you within time t? You must have had n steps of a Poisson process within that time, and the probability of that decays like 1 over n factorial, and that decays faster than the exponential growth of the number of paths. So you don't have influence propagating from infinitely far away over finite time. There's only some large random but finite set that can influence you. Yeah. No, so there are two. It's clear that starting in A union B, you get a bigger epidemic than starting in A alone or starting in B alone. But what you get is smaller than if you add them together. Oh, I see what you're saying. Yes, yeah, you're right. So it is indeed equal. Yeah, it is equal. Yeah. Yeah, you do get equality. Yeah. Okay. Yeah. Yeah, if you count the number of infected vertices, it's subadditive, but as a set, it's equal to the union. That's right. Yes. Okay, good point.
I'm going to try this. Work it all. These things on the table.
It seems to work.
I have a question nevertheless. What is the stochastic formal statement for
Okay, I should be, yeah. So on this realization, it's an almost sure statement. So you're asking what's the stochastic version? Okay, so yeah.
the monotonicity? I thought of like this: like vertex X, probability at time T, if A was the initial set,
Yeah.
Being infected is less than if B was the initial set. That's
Right. Yeah. That's what I was. Yeah.
translate similarly to this.
So what you could say is that the probability that X is in psi A union B of T is less than or equal to the probability that X is in psi A T plus the probability X is in psi B T. There's no equality anymore. So this is, yeah, a subversion which is subadditive. I don't think so. I think it'll be bigger than the maximum. Yeah, because, yeah, it'll be bigger than the maximum. You could get infected from either of them. They are overlapping events. They are not disjoint, but both of them contribute to the probability. Okay, and one last thing you can get from this construction is duality. So what does duality say? So the probability that if you start in set A, that some vertex in B is infected at time t. So you cut starting with A being infected, run the process up to time t, ask what's the probability that somewhere in B there's an infection. This is the same as the probability if you start in B. Sorry, that this is non-empty, that this. The probability the intersection is non-empty, so the probability that starting in A, there's infection in B, is the same as the probability starting in B that there's infection in A at time t. Not empty. Not. Yeah, thanks. What do you mean by the measures of? I guess there's some kind of description of that in terms of applying this to different sets B, but all I mean is the probability if you start an infection in A, you will have infection in B at time t is the same as if you start an infection in B and ask if A is infected. So in particular, starting an infection at a single site X and asking, is there infection anywhere in the graph at time t? Is the epidemic not died out at time t? Is the same as starting in the initial condition where everybody is infected and asking what's the probability that your specific site X is infected at time t. Okay. And why are these two things the same? Well, they are the same because the Poisson processes are all reversible in time. If you run time backwards, a Poisson process looks exactly the same. So in terms of this construction, you cannot tell whether the arrow of time goes that way or goes this way. Everything looks exactly the same. So starting at A, running up to time t and looking at set B is the same as starting at B at time t, running back down to time 0 and looking at set A. Yeah, this very crucially depends on the graph being undirected. Otherwise, reversibility breaks down. Okay, so that's the construction of the contact process. That's the graphical construction of the contact process. Okay, so this model has been studied in a number of different disciplines, both in mathematics and in statistical physics and theoretical computer science. So I don't fully know what the motivation was for physicists studying this. My guess is it has something to do with the Ising model, but I don't know exactly what. Maybe someone in the audience knows that. But let's look at what are some of the questions people have asked about this model and what do we know about it. So the version that was studied most classically is this model on ZD, on the integer lattice. So, but more generally, what are the kinds of questions we are interested in? So let's start. So the most basic question maybe that we could ask is, does the contact process become extinct? Or does it persist forever? So a bit more precisely, is there a random time t such that starting from the initial condition A, psi A at this random time t is equal to the empty set with probability 1. So that corresponds to the process becoming extinct. And if that doesn't happen, we'll say it persists. And in a little while, we'll look at a more detailed notion of persistence. Well, this is going to depend on the set A. So let's first look at what we know on ZD, which was the first graph to be studied. Okay, so let's start with a very trivial observation to get rid of one of the cases. If we start with an infinite number of infected vertices, then it takes exponential 1 time for each one of them to recover. So the maximum of infinitely many exponentials is infinite. So there's no way it can become extinct. So there's no work to be done there. Yeah, that's a straightforward observation. Then at any time, at any finite time, you're going to have infinitely many infected vertices. So you don't have extinction in this case. So it's only interesting to look at finite initial conditions and what happens in that case. So the first result is by Harris, and it says that if your infection rate is small enough, if it's smaller than 2D minus 1, so D is the dimension, 2D minus 1 is your number of nearest neighbors. So if lambda is smaller than, should be 1 over that, then extinction is guaranteed. Then with probability 1, you become extinct from any finite initial condition. And this was shown by Harris, 1974. Yes, I think so. I'm not 100% sure. Oh yeah, that's true for bounded degree. Yes, that's true for bounded degree. Yeah, so Harris didn't prove it that way, but one way to prove this is to dominate the epidemic by a branching random walk, and that would give you this result on any bounded degree graph. And the other thing Harris showed is that if lambda is big enough, then starting from some non-empty initial condition, let's say start with just the origin infected, so what's the probability that you never become extinct? So the epidemic started with just the origin infected is non-empty for all t. Well, the probability of this event is strictly positive for big enough lambda. Okay. Also the same. So maybe now's a good time to draw a graph. So I have the infection rate lambda on the x-axis and the probability of non-extinction on the y-axis. And what Harris's result says is that at least up to some point, the probability of non-extinction is 0. Extinction is guaranteed. And for large enough lambda, it's strictly positive. Okay, we have monotonicity, so it will do something like this. S1. But we don't know what happens in between. So finer versions of this result were shown by two people. So first, let me state the result. In fact, what's true is that there is a critical value of lambda such that if lambda is smaller than lambda critical, then P extinction equals 1. And if lambda is bigger than lambda critical, then this probability is strictly smaller than 1. Okay, I guess by monotonicity you can already see that. So it's saying, what it's saying is that you have to have some value lambda critical here, such that above this, the probability is strictly positive, and below it's 0. I suppose this lambda critical doesn't depend on the initial set, so that's the point. It's not. It's the same no matter what finite initial set you choose of infected vertices. And there's still the question: what happens at lambda critical? Is there a jump, or is it exactly equal to 0? And it's known that it is 0. So what you have is a picture, something like that. Okay, and these results were proved by Duret in 1980 for the one-dimensional lattice, and by Besweden, Huth, and Grimet. In 1990 for the general case. That lambda critical is the same regardless of the starting set A, so long as it's finite. Yeah. No, we don't. Lambda critical, this gives a bound on lambda critical, so this tells you it's bigger or equal to 1 over 2d minus 1, but it's not exactly equal to that. Okay. This is only known for ZD. That this bound works for any bounded degree graph is true, but in the opposite direction, it's not the case. So we'll look at results for the D-regular tree as well, where something more interesting happens. And yeah, even for bounded degree Galton-Watson trees, things aren't known. On finite graphs, it's always going to become extinct. Yeah.
The 1990 result, does that actually hold for any amenable graph, one where the ball grows?
I'm not sure. I'm not sure. There are results, right, on amigo? Okay. Okay. But that was later, I guess. Okay. So it's 10:30 now. When do you want to? 14. Okay, good. Okay. Yeah.
So even though extinction is certain on planet graphs, you could ask for a similar threshold theorem about when on certain families of planet graphs the time to extinction grows exponentially with the size of the graph.
Yeah, I'll be speaking about that later. Yeah. Yeah, it's yes. So that comes from that result. It's not zero and it's not infinity. Those two things are not trivial. Yeah. Sorry, in? Yeah. But the mean field theory is not always correct. So that's kind of the point of a lot of this. Yes. Okay, so we define persistence. So extinction means that there's some random finite time at which the epidemic disappears. You reach the empty set, and we define persistence as the opposite of that. But there's one more possible way of defining persistence. So let me state that. So I'm going to define two notions of persistence, and so two critical infection rates corresponding to those. So let's define lambda 1 the way we did as the smallest lambda for which if your contact process with rate lambda satisfies that for all t the infection started with just the origin infected is non-empty. So the probability of this event must be strictly positive. So what's the smallest lambda for which you have positive probability of surviving forever? That's what we defined. But what might happen on ZD is that the infection might survive forever, but it might, if you start off with the origin being infected, it might drift off to infinity, where the infected set might wander off to infinity. And maybe infection never comes back to the origin. So you could define a stronger notion of persistence and ask, does the origin itself get reinfected infinitely many times? And so we define lambda 2 to be the threshold for that. So it's the smallest value of lambda such that, okay, so let me do this in words. The origin is in psi naught t okay, maybe I should just do it formally. For all capital T, there is a small t bigger than that, such that psi naught, such that the origin is in psi naught t. And this event happens with positive probability. So give me a time capital T as far in the future as you like, and sometime after that, the origin will get infected again. So it gets infected infinitely many times. So what can we say about the relation between these two critical parameters? What's clear is that if the second event happens, then the first event clearly happens. If the origin itself gets infected infinitely many times, infection can't disappear. So it's obvious that lambda 1 is less than or equal to lambda 2. Okay. Are they in fact the same? Well, it turns out that on ZD they are the same, and in fact these two papers showed that as well. They showed not only that the epidemic has positive probability of surviving forever, but that conditional on this event, the origin gets reinfected infinitely many times. So on ZD, they are in fact the same. So there's only one threshold, though in principle there could be two, that there is only one. Maybe there's nothing special about ZD. Maybe this is what always happens, that you always have only one threshold. Well, that's not true. It turns out that on trees, you do have two thresholds. So let's now move on from ZD to look at some other graphs. Well, I'm just going to look at a couple. So the deregular tree, as I mentioned, is, okay, let me just draw it differently this time. So here's the three-regular tree. There's some distinguished vertex, which we call the root, but it's not a finite tree. It's not the root in the usual sense. So here's our three-regular tree. So as usual, you go down, branching by 2 at each step. But here you also go up. And there are all these vertices above you as well, or which you reach by going above. This is the infinite three-regular tree. This is, we'll call this the origin. You can pick any vertex and call it the origin. Okay. And this, so TD is the deregular graph. Sorry, deregular tree. And it's known that lambda 1 is strictly smaller than lambda 2 on TD. So there is an intermediate phase in which the epidemic survives forever, but it drifts off to infinity. And somehow there's more space on the tree for this to happen than on ZD, so it's maybe intuitive that that's possible. And this was shown for D bigger or equal to 4 by Pimentel in 92. D equals 3. Okay, and D is bigger or equal to 3. That's the case for which I'm stating the result. If D equals 2, for the two-regular tree, this graph is just Z1. It's the one-dimensional integer lattice, so we are back to the old result. So it's only for D bigger or equal to 3. And this was shown by Liggett in 96. And there was a very nice unified proof of both these results by Alan Stacey in 96. So I said I won't say much about proofs, but maybe I'll say a tiny bit about his proof because it's very elegant and it gives you a little bit of a flavor of how you try to prove results like this. So let's just say these are just the ingredients of proof that number one is one. Okay, so what he did is he associated a weight with each vertex. So you divide your vertices into levels. You start at level 0. Your root is at level 0. Its children are at level 1. Grandchildren at level 2. And so on. But the graph also extends above, so its parent is at level -1, along with other nodes, level -2, etc. And the weight of a vertex, so pick some alpha positive and define the weight of a vertex to be Wx is. So the weight of a vertex is alpha raised to the level of the vertex. And then the weight of a set of vertices is the sum over vertices in that set of the weight of x. And now this process here has some very nice symmetry properties. So if you start it off not at the origin, but at some other vertex x here, then the weight process evolves the same as if it was started at the origin, but multiplied by w of x. Okay? So by shifting the levels, you are just adding a constant to all the levels. So you are multiplying by the same alpha to the Lx. So the process started anywhere else is related to the process started at 0 by just multiplying the weight. So you can use that fact, you can use subadditivity, the properties of epidemic, of the contact process we looked at, and you can show that, that there's something closely related to this weight process, which is a super martingale. So not the weight process itself, but after rescaling it by something, what you get is a super martingale. Okay, so to do that, okay, you need one more thing to do that. Okay, so suppose we can find, so suppose that for some time t naught positive, we have the following, and some choice of alpha. The expected weight so you start with the origin infected, you look at the weight of the random set of infected nodes. If the expectation of this weight is some beta strictly smaller than 1, if this is true, then you can show the probability that there's some random time after which you will never revisit, the infection will never revisit the origin, such that for all T positive, the origin is not in the infected set. The probability of this event is 1. And the way you show that is by showing that beta to the minus n times this weight is a super martingale. So eventually the weight suitably rescaled converges to some limit, and so the unrescaled weight has to converge to 0 over time. That's the idea. So this random set, you start with weight 1 with just the origin infected. It's spreading out, and by spreading out, the expected weight is decreasing, and it has to decrease to 0. And if you revisited the origin, it would have weight 1, so that's not consistent with it decreasing to 0. So you show that, and thereby you show that for this value of lambda, you're not going to have strong persistence. And then you have to show that you can also choose a lambda such that you have weak persistence at that, but not strong persistence. Okay, so I won't go into the details of that, but so that's how Stacy showed that indeed there's a separation between these two values of lambda. Okay, yeah, I'm also out of time, I think, yeah.
You can't get from one configuration to some other inputs as exponential potential function. It has that flavor, so is this very common in these stochastics?
Yeah, I think the terms potential function, harmonic function, and martingale are all much the same thing. So, yeah, and a super martingale is something where the potential is decreasing. If it's constant, it's a martingale. So. At criticality, so no, I don't know. On ZD, we don't have, there's no jump, so I would expect there's no jump, but I don't know. Okay, so I'm out of time, but I guess the only other thing I wanted to say is that the next step, perhaps to look at going on from trees, is to look at, from regular trees, is to look at Galton-Watson trees. And already there, we have no general results. In some specific cases, there may be results, but there are no general conditions on which these two thresholds are the same or separated. It's not known. Okay, so we can take a break there.
You take a 10, 15